Okay, this continues our lecture on the central limit theorem. We're doing this example, the random sample of 64 taken from a normal population. Since it's a normal population, we don't care what size the sample is. However, the sample is over 30, so it would work even if it wasn't a normally distributed population. So our mean is 51, and our standard deviation is 6.8, and our sample size is 64. So our first one says, what's the probability that the sample mean will exceed 52.9? So here you have x bar sample mean exceeding 52.9. So I've applied the central limit theorem by subtracting the mean of the population and the standard deviation divided by the square root of n, arriving at 1.65. Now, because I'm in the right tail, that's comparable to doing a left tail lookup, so I'll go ahead and I'll go over to my table and we'll look that up. So a 1.65, so here's 1.6, and the 1.65 would be right there. So we have 0.0495. So my probability is 0.0495, and that would be the probability of getting an average in this population that's 52.9 or larger. Now part B says that we want to fall between 50.5 and 52.3. So for that one, I have standardized each of my scores by subtracting the mean of the population, dividing by the standard deviation of the population, divided by the sample size, and I've come up with being between a negative 1.18 and a 0.94. Now that, in order to find it using a negative z table, I have to consider the area in this right tail and this area in this left tail. And the area in the right tail, remember, is comparable to if it were in the left tail. So what you see is I take the whole distribution, subtract the area in the left tail and the area comparable to what would be in the right tail, and that will give me my probability. So I'll go back to my table and I'm looking up a 1.18. So 1.1 and then 8, and that would be 0.1190. So 1190 is my probability there, and then 0.094, so 0.09 and then 4 there. So there's my 4, and my probability is 0.1736. So 0.1736, and then I can go to my calculator and I can do this probability. So I have 1, and then I'm going to subtract 0.119, and then I'm going to subtract 0.1736, and I will get 0.7074. So my probability is 0.7074. So 0.7074. And that would be for my second one. Now for part C, what I have in part C is that I want to be less than 50.6. So this is my average is less than 50.6. So in that one, again, I'm going to standardize. This is the picture that I'm looking at, right? So I'm going to have some z over here, and I'm going to be looking here. And so this is the z that I'm going to be looking at that I want to be less than. So I'll have the probability that my x bar minus my mean divided by my standard error, the sigma divided by the square root of n is called the standard error, is less than 50.6 minus 51.5 divided by the 6.8 and then divided by the square root of 64. And once I find that value, then I'll do a direct table lookup, so the probability that my z is less than, and it's going to be some negative value. And once I look that up, then I can look it up in the table. Now I'll let you go ahead and do that one on your own. In a minute I'll go look it up and get it finished up, and that way you can compare. But let's take a look quickly here at the very last part of the example. What's the probability that a single observation would be below 50.6? Now this one's different. This is not the average, it's a single x. So here what I want you to notice is that we had an x bar. Here I want a single random variable, so I have just an x, and that's the difference between those. So there's not going to be any difference in my value. There's going to only be a difference in my standardization to get my actual values. So my 50.6 minus 51.5, that's not going to change. What's going to change is the only thing I'm going to divide by is 6.8. So here my value is going to be 8 times larger than this one. So 8 times larger means that it's going to be way out here in the tail, right? This one is going to be much closer. So the probability of a single random variable being out in the tail is much greater than the probability of a random sample having an average that's that far out in the tail. So now I'm just going to pause and I'll go calculate these. And what you see here is that the probability for the average is negative 1.06, and this one's 0.13. So this one down here is much closer to 0, and this one's way out here away from 0, which means our probability here is going to be much less than the probability here. And now we'll go look those up in our tables. So our table here at negative 1.06, that gives us 1446. So this probability is 0.1446. And that's opposed to my probability here of a negative 1.13, so negative 0.1 and then the 3 over here, and that'll be 0.4483. So 0.4483. And so what you see here is the probability of this single observation being much greater than the probability of a random sample having an average that's less than that. And that's the whole idea behind the central limit theorem. So I think that we probably pretty much got that. And now what we're going to do is we're going to apply the central limit theorem and combine that with our idea of the inverse normal. I think I'm again going to leave this for another video, and we'll start another video there.